Okay, today we're very happy to have Geoff Penington, who's going to tell us about type II von Neumann algebras and quantum gravity. Take it away, Geoff.
Okay, awesome. Well, thanks very much for inviting me to talk. So yeah, this is going to be a sort of high-level overview of few papers I've written this year with some combinations of Edward written. I mean, I guess we're also going to be talking about a paper Edward wrote before I was even involved. Then Chandrasekaran, two of the papers, and Roberto Longo on one of the papers. And so all of this work involves this technical mathematical concept of the type II von Neumann algebra, and using it to say something about quantum gravity, in particular about sort of entropies of black holes and cosmological horizons, and their relationship to what's called generalized entropy. So let's start with that. So what is generalized entropy? Well, as we all know, the horizon area of a black hole appears to be related to some sort of entropy by this famous Bekenstein-Hawking formula, area of the horizon over 4G. But of course, renormalization of G means that this area 4G formula needs to be renormalized, and where it's renormalized is by adding the entropy of the bulk matter nearby, the entropy of all the matter fields outside the horizon. That gives us some quantity called generalized entropy over 4G plus this entropy S bulk that's supposed to be UV finite. So this is supposed to be a well-defined finite thing in non-perturbative quantum gravity. So there's sort of some standard law that says that this generalized entropy is in some way counting the entropy of both the black hole itself, that's the A over 4G part, plus everything outside it, that's the S bulk part. But what we actually mean by that is sometimes less clear. So for extremal black holes in string theory, then this A over 4G formula can be derived by a very explicit counting of individual microstates, by we flow to recoupling when they're not actually a black hole anymore, but you argue that the count is the same because of supersymmetry, and then it really is just counting something. In ADS CFT, we have the QES prescription that sort of makes this precise, that this is for an appropriate boundary region. This is a formula for computing the boundary entanglement entropy. But the sort of known derivations of that formula use Euclidean gravity path integrals in the replica trick. And in the boundary, those path integrals sort of make sense as computing an entropy, and we know what the entropy means. But in the bulk, they're a bit weird because the sort of thermal circle contracts. We think we understand the ADS CFT dictionary of just mapping partition functions, but still it's not really clear from a bulk point of view what that computation actually means. And in other settings, it's even less clear. So for example, for cosmological horizons in de Sitter space, then generalized entropy seems to be, again, computing some sort of entropy. It still has a relationship, temperature, and so on, but the meaning is even less clear than in the settings I discussed about. Okay, so let's say that we forget about string theory because maybe string theory just isn't the right description of the universe. I don't know. And let's forget about Euclidean gravity because that's always been sort of black magic, and we don't really know what it means. What do we still know about the role of generalized entropy? Well, the answer is we do know something. We still know the sort of original reason Hawking came up with A over 4G. And that's that you can derive the Hawking temperature of a black hole, you can derive Hawking radiation just using Lorentzian semi-classical gravity. So you take G to 0, you do some QFT and curved spacetime calculation, and you see radiation coming out at a certain temperature. And we also know the energy of the black hole, so then we can just plug in that D equals TdS, the famous first law of thermodynamics, the Clausius relation, really. And we find by solving that ds is equal to dA over 4G. That's just some maths you can do. And then if we assume that small black holes have some finite S and don't have arbitrary large entropy, then you can just sort of integrate up from A equals 0 and conclude that at least for sufficiently large black holes, that integral dominates over the small black hole entropy, and we have S equals to A over 4G. Okay. So that's a great argument. We declare victory. We've derived the Bekenstein-Hawking entropy. But there's a reason we don't, we don't say that Hawking fully derived Beck-Hawking in every way you'd like to. And that's because fundamentally this is a derivation in classical thermodynamics, not statistical mechanics. So, this formula is a 19th century formula that was come up with before, is a definition of entropy before there was any notion of a connection between entropy and counting something, counting amount of noise, amount of degrees of freedom, whatever you want to call it. And that's really all we're doing here. So any argument that this means A over 4G is the statistical entropy of the black hole has to be just by analogy with how ordinary thermodynamics works, and the fact that 19th century classical thermodynamics ended up being explained by statistical mechanics, but that cannot be derived. Okay, the goal of today's talk is to explain to you a way to find some degrees of freedom in just Lorentzian semi-classical gravity, so essentially the same theory Hawking was considering, whose statistical entropy is in fact equal to the generalized entropy of the black hole. So it's sort of souping up Hawking's derivation to really find it as a statistical entropy and not just as a classical thermodynamic entropy. Of course, just like in Hawking's derivation, we're still going to be in the G goes to 0 limit of gravity here. So we won't be able to resolve individual microstates because the number of microstates won't be finite. Okay, A over 4G will have gone to infinity. So all these entropies will really be infinite. And instead, what we'll find is what's called the type 2 von Neumann algebra. So this is just a rigorous mathematical formula for deriving degrees of freedom that have infinite entanglement entropy. I'm going to explain how there's a boundary interpretation of this algebra in ADS-CFT in terms of the large n limit of CFT correlation functions. Talk about how these ideas extend to semi-classical de Sitter space and what you need to do to have the same story go through there. And then briefly at the end, I want to talk about how you can move slightly away from this sort of strict semi-classical limit to considering JT gravity and the so-called disk approximation, but at finite temperature. So this means we're not having wormholes or anything like that. So the sort of ground state entropy, the extremal entropy S naught is infinite, but we're sort of finite excitations above that ground state energy. Okay. Okay, but before I can do any of that, I need to talk a bit about what von Neumann algebras are. So I'm going to try to keep this as quick as possible. So von Neumann algebras, just some bounded operators acting on a Hilbert space that form an algebras. They're closed under addition, multiplication, so on. We also want them to be closed under Hermitian conjugation. That's called a star algebra. And finally, there's a technical seeming condition that we want to be closed with respect to the strong operator topology. What this means is if you have a sequence of operators an that converges as a goes to infinity, n goes to infinity to some operator a, converges in this particular sense defined here, then and all the ANs are contained in your algebra, then the limit operator should also be contained in the algebra. So we should be able to take limits without ending up outside of the algebra. Okay, so the particular definition of convergence here is important. There's actually some nice arguments that this is the right physical notion of operators converging if you're thinking of them as measurement operators. But it's also von Neumann algebras turn out to be structurally nice, and so the nice things to think about. I want to emphasize this is only important for infinite dimensional algebras. For the finite dimensional algebra, then it will always converge to it will always be closed with respect to this topology. Okay, so there's an extra condition you might also want to impose, which is that the center of A, the operators in A that commute with everything in A, should consist only in multiples of the identity. If that's true, then we say that A is what's called a von Neumann factor. So the nice thing about von Neumann factors is that any von Neumann algebra can be written as a direct sum, or more generally a direct integral, basically a continuous direct sum, over von Neumann factors. So von Neumann factors are like the building blocks that you build von Neumann algebras out of. So just to give a simple example of a von Neumann factor, the most obvious one is just the algebra of all bounded operators acting on some Hilbert space. Okay, So this Hilbert space can either be H itself. Remember, the von Neumann algebra was defined to be some subalgebra operators acting on H, or it can be, say, some smaller subsystem, HA. So H is a tensor product of HA tensor HB, and the von Neumann algebra is just operators that act only on HA. So such algebras are known as type 1 factors. And they can be labeled up to isomorphism by the dimension of the Hilbert space HA. So we have a type 1 D factor. D is this dimension for all integer D that's either finite natural number or infinity. Okay, depending on the dimension of HA. In fact, in finite dimensions, type 1 factors are the only type of von Neumann factor you can have. But in infinite dimensions, then there's more subtle possibilities that can show up. So morally, what's going on here is that even in infinite dimensions, von Neumann factors are still sort of the algebra of operators on a subset of degrees of freedom, that we morally sort of think of as a tensor product factor, but they're just not going to be strictly a tensor product sum factor because those degrees of freedom will always be infinitely entangled with some other degrees of freedom. I'm going to give an example of that very explicitly now. So don't worry if it was sort of vague. So this is going to be the so-called unique hyperfinite type 2 factor, originally constructed by Murray and von Neumann. The idea is to construct a Hilbert space H that consists of infinitely many pairs of qubits. So each of these circles represents a qubit, and we've got a line, infinitely long line of pairs of them. Okay? But we're going to put an extra condition on states in this Hilbert space, which we really want to do because otherwise the Hilbert space is not separable. It doesn't have countably infinite dimension and everything gets very bad, which is that we want all but finitely many pairs of these qubits to be in a particular maximally entangled state psi. Okay, so here I've drawn these first 3 pairs of qubits, can be in any state you like, call it phi, some arbitrary entangled state on all of them maybe. But then this pair is in state psi, this pair is, and so on. Okay, and we allow the number that aren't in that state to be as big as we want, but it has to be finite. So there's still infinitely many that are in psi. So technically what I just described was a vector space because it can take the sum of states in this in H and still get something in H. But as I described it, it's not actually a Hilbert space because there are limits of sequences of states that have all but finitely many in the state psi that converge with respect to the inner product, but that don't have all but finitely many pairs in the state psi. Okay, so they sort of have, as you go further and further down this line, the states get closer and closer to being in psi, but they're not exactly in psi. So that's fine. It's just like the fact that square root of 2 is an irrational number, and you deal with it in exactly the same way that you deal with it for rational numbers. You take what's called the completion of this vector space, just like the completion of the rational numbers of the reals, this completion is a Hilbert space. Okay, so don't worry about technical details, but that's what you do. And then we can consider an algebra of operators acting on this that just consists of operators that act on finitely many qubits in the top row. Okay, so this acts on H nicely. Its center is sort of clearly trivial. And it's closed under conjugation. Then we have that last condition that we have to be able to take limits. And as I described it, that condition is not satisfied. But we can, in exactly the same way we took the completion of the vector space, we can take the completion of this algebra with respect to this strong operator topology, and that gives us a von Neumann factor. Okay, so for people who know about von Neumann algebras, the other way you can do this is to take the so-called double commutant. Okay, so clearly we've constructed a von Neumann factor, and morally it's the algebra of operators acting on the top row, which is sort of morally a subsystem of the Hilbert space. But the Hilbert space is not actually a tensor product of stuff on the top row with stuff on the bottom row, because there's no states in the Hilbert space that are a product state, that are state on the top row is tensor state on the bottom row. Okay, so clearly we have something new going on here. Every state in H has infinite entanglement between the two rows. So this is known as a type 2 factor. And the reason it's known as that is because it has what's called a trace. So what is a trace in this context? It just means that it's an linear functional, a positive linear functional on operators in A that's defined as follows. We just consider the state that I call capital psi. That's just a tensor product of little psi on all pairs of qubits. Okay, and then we define the trace of A to just be the expectation value of A in this case state capital psi. Okay, this is a normalized state in the Hilbert space, and we're just using it to define something we call a trace. So I want to be clear that this is not the trace of the operator A on the Hilbert space H. That's actually infinite for any A in this algebra. But we call it a trace just because it satisfies the property that for any pair of operators A and B in our algebra, trace of AB is equal to trace of BA. Okay, the trace of commutators is 0. So to see that this is true, note that if the operator A that we're taking the trace of acts on only the first n top row qubits, then the trace of A is just equal to the ordinary trace of A on those n qubits divided by 2 to the n. That's just because this state is maximally entangled on the first n pairs of qubits. Okay, so clearly for this trace, we have trace of AB equals trace of BA. So also for this trace, we do. Okay, in general, A and B can act on arbitrarily many qubits. But sort of because this is true for any number n, then it's also true for this trace up here. So morally, this trace we defined is sort of an infinitely rescaled trace on the entire top row of qubits, right? It's the trace on all infinitely many qubits in the top row divided by 2 to the infinity. That doesn't really make sense, but this thing certainly does because it's just the expectation value in some normalized state. Okay, so in a von Neumann factor, it turns out that a trace, if it exists, is just unique up to possibly rescaling it by constant. And so this is the sort of only trace we can find. But this trace has an interesting property, namely that unlike the usual trace on an infinite dimensional Hilbert space, this trace is finite for any bounded operator. So for example, on an infinite dimensional Hilbert space, the usual trace, the identity, is infinitely big, and only so-called trace class operators, things like projectors onto a single state, have finite traces. In this case, the trace, the identity, just equal to its expectation value, which is just 1. Okay, so this is very different from the trace on a usual trace on a type 1 infinity algebra. Because the trace, the identity is finite, and is in fact 1, we call this a type 2-1 factor. So the type 2 says it's not type 1, but it does have a trace. The 1 says that that trace is finite for any bounded operator. Because we can define a trace for this algebra, we can also define density matrices on the algebra for any state phi. Okay, so this is just defined in exactly the usual way as the unique operator rho phi that is contained in the algebra, such that for all operators A in the algebra, the trace of rho times A is equal to the expectation value of A in the state phi. Okay, this is just completely the usual definition. It's just the meaning of trace has changed somewhat. And then, of course, if we can define a density matrix, we can define an entropy by the usual formula that the entropy is just trace of rho log rho. So let's consider an example. Let's take this maximally entangled state, ket psi. Okay, so by definition, the trace of A itself is equal to the expectation value of A. So that means the density matrix, this maximally entangled state, must just be the identity. Note that unlike in sort of a usual trace, it would normally be like the identity divided by the dimension, the Hilbert space. Here it's just the identity. There's no other factor. So then we can compute the entropy of this thing. It's minus trace of rho log rho. Log rho is 0 in this case, so the entropy is just 0. So the maximally entangled state has 0 entropy. If you're not familiar with this seems kind of confusing. But it's completely okay. Maximally entangled just means it has the largest possible entropy. It turns out that any state has entropy less than or equal to 0. Okay, with respect to this trace defined in this way. So what's happening here is the following. Because this trace should be thought of as being like infinitely renormalized, infinitely rescaled, then the density matrices are also getting infinitely rescaled. If the density matrix is infinitely rescaled, the log of the density matrix infinitely shifted by an infinite constant getting subtracted. Okay, so what that's doing is it's subtracting off this universal infinite divergence that all states have, and it's just leaving some finite number, which is the entropy deficit of that state relative to the maximally entangled state. So that's why it's less than or equal to 0. Okay, great. We're getting through this von Neumann algebra stuff. I promise we'll get to some physics soon. But there's another type of type 2 factor we can define called the type 2 infinity factor. And these can be made by a very simple way by just taking the tensor product of the type 2 factor with the type 1 infinity factor. Okay? So clearly this is not the algebra of bounded operators on some Hilbert space subsystem. So it's not type 1, okay, because it has this type 2 factor in it. It has a trace. So if it's not type 1 and it has a trace, we call it type 2. And that trace is just defined by taking the tensor product of the trace in the type 2 algebra with the trace in the type 1 infinity algebra. Okay, that defines a trace in this product algebra very simply. However, unlike for the type 2 algebra, the trace of the identity is now infinity. Okay, it's infinity because the trace of the identity is infinity on the type 1 infinity algebra. So this algebra isn't a type 2 factor because it doesn't have a finite trace for all bounded operators. Instead, we call it type 2 infinity factor. Can define density matrices and entropies for type 2 infinity factors, just like for type 2 factors. However, there's a difference that there's no maximally mixed state anymore. There's no sort of maximum entropy state with the identity density matrix. And that's because the trace of the identity is infinity, so it's not a normalizable state. Okay, so another thing about density matrices on type 2 infinity factor is for the type 2 factor, there was a sort of canonical normalization of the trace, where the trace of the identity was 1. For type 2 infinity factor, there's no obvious normalization to use. It's sort of arbitrary. And so that means that the entropies are sort of arbitrary up to a constant state independent shift. Okay, there's no natural way to fix the normalization of the trace, and hence this shift in the entropies. Okay, we're almost done with our lightning review of von Neumann algebras. So the last type of von Neumann algebra is a type 3 factor. And this is what shows up is we will replace this state psi in our construction of H by some other state psi prime that's entangled but isn't maximally entangled. Okay, or we can also do other fancier things like replacing it by multiple states psi prime that sort of, alternating ones, maybe alternating pairs of different, or replace the qubits by qubits with some complicated state. There's a lot of things we can do. They all basically give type 3 factors. Everything goes through the same way. We get a von Neumann factor out of it. But the state psi prime, tensor psi prime, so on, is not tracial, okay, because it's not maximally entangled anymore, or the psi prime is not maximally entangled. And similarly, the state we used before to define the trace is just not contained in the Hilbert space because it doesn't look like psi prime for all but finally many states. Okay, so it turns out there's just no way to define a trace on such an algebra. It just doesn't work. And heuristically, what's happening here is that in the Hilbert space H, the 2 rows of qubits are now not only infinitely entangled, but there's sort of infinite fluctuations in their entanglement. Okay, so if you imagine this psi prime is like a thermofield double state at some finite temperature, then the sort of amount of entanglement is like the total energy of each top row of qubits. In a thermal ensemble, in the large thermodynamic limit, the expected energy becomes infinite. That's saying it's infinite entanglement, but also the fluctuations in the energy become infinite as well. Okay, and so that's why there's infinite fluctuations in the entanglement. Okay, so as I said, these algebras are type 3 factors. So that's the last type of algebra that's going to show up. And the reason we're going to be needing these type 3 factors is it turns out that they're the algebra associated to any subregion in quantum field theory. Okay, so in quantum field theory, at the edge of a region, there are an infinite number of Rindler modes. Those Rindler modes are thermally entangled. It's like having this psi prime that's sort of not maximally entangled, but is entangled. You have infinitely many modes of them. And so that gives us a type 3 factor. Okay, that is the maths section of the talk done. I sort of did it at lightning speed to not bore you. If you got completely lost, then please shout any particularly pertinent questions at any time. But yeah, we're now ready to talk about some black holes, so that's exciting. Okay, so what we're going to try and do is we're going to try and study sort of perturbative quantum gravity around a fixed black hole background in the strict limit of G goes to 0. Okay, so in that limit, it basically almost just becomes quantum field theory in the fixed background. So, you still have like graviton fluctuations, but those are just some free spin 2 field, and you can basically treat that as just an ordinary quantum field theory thing. But there is one extra mode for the two-sided black hole that can sort of survive to the G goes to 0 limit without well, still leaving the background fixed, but can't be described by perturbative quantum field theory. And that's what's called the time shift between the left and right boundaries. Okay, so what do I mean by this? So just think about ADS-CFT. The thermofield double state is dual to the two-sided black hole. But the time-evolved thermofield double state, where we evolve one boundary forwards in time, is a distinct physical state, and it's a distinct physical state in the bulk as well. Okay, so what we mean by this is that the boundary time is some physical degree of freedom. It's not just a gauge degree of freedom because it's at the asymptotic boundary. And so if you start at sort of boundary time 0 up here, and then you head straight through the black hole, pass through the bifurcation surface, and come out the other side, you won't necessarily end at boundary time 0 on the right. Okay, you'll end up some other time. There's a difference between the two times, and that is the time shift. It's some physical additional mode that you can include in your Hilbert space. That with the background is still just a black hole, but it's this extra a large gauge transformation degree of freedom. So this degree of freedom is conjugate to both the left and right ADM masses of the black hole. Okay, so the ADM masses are like the boundary Hamiltonian ADF-CFT, the time evolve you forwards, so they generate translations of this time shift mode. I say they're both conjugate to it because the difference between the left and right ADM masses doesn't actually change the time shift at all. It commutes with the time shift. What it does is it acts as a boost of all the quantum fields sitting in here, right? So we time evolve this forwards, time evolve the right boundary forwards and the left boundary back. Then we can do a gauge transformation that leaves the boundaries in the same place, but just boosts the bulk quantum field sitting in the middle. Okay. Okay. So our full Hilbert space then is the QFT Hilbert space, tensor this extra L2 of R degree of freedom that describes this time shift mode. Okay, we can always choose a gauge where we think of the time choose a gauge where we think of the right boundary time as being fixed, so that the sort of t equals 0 on the right boundary is always in the middle here, and it's just the left boundary time that fluctuates. Okay, so then we have some wave function f of t that sort of describes the left boundary t equals 0 point and how it fluctuates in this fixed geometry. Okay, that's the time shift mode. Okay, so we now want to define the algebra of all observables within this sort of semi-classical Hilbert space that can be seen from the right boundary. Okay, so that's generated by two things. The first thing is generated by just sort of QFT observables that are localized in the right exterior. The second thing is that we also have the right ADM mass at infinity. Okay, that is localized to the right boundary, and so it should be included in the algebra. Okay, so there's a couple of qualifications to each of these things. The first is that these right exterior QFT observables need to be dressed. Okay, to be gauge invariant, they need to be dressed to some asymptotic boundary, and in particular to be localized in the right exterior, then they should be dressed to the right boundary. Now we chose a gauge where the right boundary was sort of fixed. So that's sort of trivial, right? We're using coordinates for the bulk that are automatically dressed to the right boundary. So just ordinary QFT operators in the right exterior automatically dressed to the right boundary. But if we want to talk about the left exterior ones, then they wouldn't be dressed to the left boundary. They'd naturally be dressed to the right boundary. So if we wanted to dress in the left boundary, we'd have to conjugate by the time shift. So I'm not going to get into that more, but that's a side comment that this is important.
Geoff, can I ask a question?
Yep.
The ADM mass on the right, I mean, we have some formulas for that in terms of asymptotic metric. And
Yeah,
so naively, it sounds like it's part of the
yeah,
set
yeah.
of observables.
It's a scaling thing. It's a scaling thing. Let me answer that question in just a minute after I talk about some other subtlety with the ADM mass, but I will explain why it's not just a QFT thing. Okay, so the other thing about the right ADM mass is that the G goes to 0 for a fixed size black hole and the ADM mass goes to infinity. Okay, so what we want to do is to, we want something finite that makes sense. We can do that just by subtracting off the sort of reference ADM mass of the black hole. Okay, so they call that E0. So that's infinite, and this is infinite. But the difference between them we can make be finite. Okay, so yeah. So now let me answer Mark's question. So the ADM mass looks like, let me get this right. It's 1 over G times the metric, or times derivatives of the metric. And so HR is actually determined by order G perturbations in the metric. Okay. The QFT graviton degrees of freedoms are order square root G perturbations in the metric. So they sort of can't see the variation in the ADM mass. The variation in the ADM mass is an extra additional operator on top of that. But yeah, great question. Thanks for clarifying. Okay, so let's just think about the QFT observables on their own. As I said, this is some subregion. Okay, it has an edge here. So these things form a type 3 factor. Okay, has no trace and it has no rigorous notion of entropy. Of course, we define entropy for QFTs all the time, but sort of we do so with a hand-wavy load of subtractions of divergences and stuff. It's much less well-defined than for a type 2 algebra. Okay, what happens if we add in this one extra operator, this renormalized ADM mass, little hr?
Sorry, can I quickly ask another question? Now that I've understood that, so the ADM mass is kind of changing the background in a sense that all these fluctuations are living on, or it. Let's see. I mean, in some,
it's a smaller variation in the background than the graviton perturbation. So we're allowing order square root G graviton fluctuations, and the ADM mass is actually smaller than that. So yeah, it's not making the background less fixed to include it. Like,
right.
I mean, it always has to change, right? If we excite stuff,
right.
Even if we're not including it in our algebra, then it's still changing as a function of, but it's really not changing very much. That's sort of why in the G goes to 0 limit, the graviton excitations can be localized and all the other excitations can be localized. It's because the graviton, the order square root G perturbations in the metric can't see the change in the ADM mass. But it is there and it's localized to infinity, so it's natural to include it in your algebra. Okay. Great. So what does little hr do? So we can write little hr as little hl, the renormalized left ADM mass, plus this boost operator for the quantum fields. Okay, little hl commutes with all the quantum field theory operators because quantum field, we chose a gauge where the quantum field theory operators address the right boundary. Okay, so it doesn't do anything to HQFT, and it generates translations of the time shift. So it just acts as the momentum operator on L2 of R. Okay. H, meanwhile, generates boosts of the quantum fields. So it turns out that adding an operator like little hr to your algebra is something that shows up in the mathematics literature. It's something called a cross product. Okay. Formally, it's the cross product of the QFT algebra by the group generated by this boost generator. In fact, this boost generator generates a particularly interesting mathematical construction called a modular flow. Technically, it's the modular flow for the Hartle-Hawking state, the sort of the vacuum state, basically, the two-sided vacuum for this black hole. Okay, don't worry about what a modular flow means if you're not familiar with it. If you are, it's probably an obvious comment. But turns out that the cross product of a type 3 algebra by a modular flow is something that mathematics people got very excited about, starting with Takasaki back in the 1970s. So just to give you a bit of history, back in the day, mathematicians hated type 3 von Neumann algebras. So von Neumann defined them, he classified all the possibilities, but type 3 von Neumann algebras were basically totally unfashionable. No one cared about them at all. They were sort of ugly. You couldn't do anything with them. They were just like structurally disgusting. No one knew how to classify them or anything. Type 2 ones were great. People, loved working on them. They were super beautiful, particularly type 2-1. And then Takasaki turned along and he showed that if you take a type 3 algebra and you take its cross product by modular flow, you get a type 2 algebra. In fact, if it's cross product to type 3-1 factor, which QFT algebras are, it's a particular type of type 3 factor, you get a type 2 infinity factor after doing the cross product. So this type 2 infinity factor has a trace. In fact, it turns out you can write down this trace very explicitly. The following, so the trace of some operator A, this A should be thought of as a function of both HR and the QFT observables, can be written as the integral from minus infinity to infinity of HL. So HR is HL plus an operator on the QFT algebra times e to the beta HL times the expectation of this operator A in the Hartree-Hawking state psi. Okay, so this expectation value, remember, A is a function of both QFT operator and HR is a QFT operator plus HL. So this whole thing in general is a function of HL. Okay, in fact, it needs to be a function of HL if this integral is going to converge. So for example, if A was just a QFT operator, then we just have integral of e to the beta HL times a constant, that would be infinite, and it wouldn't have a finite trace. So that's good because that's in a type 3-1 factor, and type 3-1 factor is not going to have a trace. But you can construct other operators, say something like a QFT operator times e to the minus 2 beta HR, something like that. Okay, then this expectation value would give you, didn't want to just be, you want some function of HR that stays finite as HR goes to minus infinity and goes to 0 exponentially as HR goes to plus infinity. Okay, so that kills off the divergence from HL going to plus infinity. Okay, so let me give an example of that will hopefully make it clearer. And the point of this example is that, if we have a trace, we can define entropies. So this algebra has very nicely defined entropies. But we'd like those entropies to be equal to generalized entropy, right? That was the whole goal of this. It was to find some algebra, show that the algebra of the exterior has an entropy equal to the generalized entropy of the exterior. So it turns out you can show for a very large class of what we call semi-classical states, basically states where the fluctuation in the time shift is very small, then this entropy, the entropy defined on this type 2 algebra using this trace, is given by the generalized entropy formula of the expectation of the area of the horizon over 4G plus the naive QFT entanglement entropy of stuff outside. Should say there's also minus a divergent infinite constant. That's just how type 2 entropies work. So that's what we should expect to exist. Okay, so in general, the proof of this result is somewhat technical. Uses a lot of sort of Tomita-Takasaki theory. I'm not going to get into it. You can read the most recent paper I wrote with Ben and Edward for details. But in a particular simple case that was actually considered already by Edward in his paper last December, which is a state that has a wave function that just looks like the Hartree-Hawking state times some wave function for HL. Okay. Turns out it's pretty easy to see that the density matrix of this state, so the operator rho such that the trace of rho times A is equal to the expectation value of A for any A in the right boundary algebra, it's just given by the modulus of this same function f, but now of HR rather than HL, all squared, times e to the minus beta HR. Okay, it's an exercise, but a very simple exercise to show that that's the right density matrix. And if we then just plug in, we just take the expectation of minus log of this thing, which gives us the entropy, we see that it's just very simply the expectation of beta HR plus the expectation of log of the modulus of f of HR squared. Okay. In the Hartle-Hawking state, the boost operator is 0, so HR is equal to HL. But this first term, first law of black hole thermodynamics, says that if you don't have any matter excitations, then the ADM mass, small linear changes in the ADM mass are just proportional to small linear changes in the horizon area. And the relationship is such that beta HR is equal to A over 4G. So this first term is exactly the expectation of A over 4G minus an infinite divergent constant, which is just this divergent constant up here. Okay, A naught is the sort of reference area of the black hole horizon. Same as equivalent to E naught. Okay, what about the second term? Well, that's just the sort of entropy of the fluctuations in the horizon area. Okay, so if the horizon area varies, horizon area has a sort of wave function that's the same as f, and this controls the fluctuations and the probability of it having a certain area A. Okay, so that's actually sort of the only part of S bulk that actually varies depending on this function f for wave function this form, because we're fixing all the matter stuff to be in the Hartle-Hawking state. And so in this simple condition, you can think of this as basically being S bulk. Okay, for general states, S bulk is a lot more interesting. This formula is more interesting, has an extra sort of relative entropy term in the type 3 algebra that makes everything work. I encourage you to look at there's a whole section in the paper we do explaining how it works, but it is quite technical, and so I'm not going to try to talk about it here. I have way too much to talk about anyway. Okay, so so conclusion is we've defined some bulk algebra in the semi-classical limit whose entropy is equal to generalized entropy. It'd be nice though to also understand what this is from a sort of CFT boundary side. Turns out that's very simple to do. It's mostly done already last year by Leuthauser and Liu. So the idea is simple. Bulk quantum fields are dual to single trace boundary operators in the CFT. Okay. Correlation functions of those simple trace operators have a well-defined large N limit. And that means you can basically just take the data of the large N limit of the correlation functions and use that to define a GNS Hilbert space, basically starting from the thermal expectation values. I'm not going to go through the details of how this works, but it gives you some sort of large N Hilbert space that describes states formed by acting with products of single trace operators. And this Hilbert space is acted on by type 3 algebra generated by the single trace operators. So this type 3 algebra is dual to the bulk QFT operator. And then if we work in the microcanonical ensemble, then the operator that consists of the right boundary Hamiltonian minus E naught also has a well-defined large N limit. So we can also define that as a large N operator acting on a large N Hilbert space. And together they generate exactly the type 2 infinitive factor we just described in the bulk. Okay. And the entropy you can show is just related to the large N limit of the usual CFT entanglement. So I should say, if you instead work with the canonical ensemble, this is what Edward did in his paper. Then in the leading order limit, you instead get a type 3 algebra with a large center. And then you can look at perturbative corrections, and those perturbative corrections sort of look like the cross product. You can sort of define entropies in a perturbative way, but it's much less nice to deal with than the microcanonical ensemble, where you really do have a type 2 algebra. Okay, so don't worry too much about those details there. That was just advertising stuff we talk about in the paper. What I want to talk about a bit is how this all works in de Sitter space. So in de Sitter space, if I have some observer, say sitting at the north pole of the space, then they have some causal patch, some static patch that they can see. That's bounded by some horizon, and the generalized entropy of that horizon again seems to have some sort of interpretation as entropy. So we'd like to argue that it's in fact the entropy of everything that can be seen by this observer going along this world line. Okay. So let's try and figure out what that algebra is. So the observer can measure sort of quantum fields that are sitting near their world line, that are on some very small neighborhood of their world line. So that's sort of naively the algebra, the algebra we're interested in. But it turns out there's a theorem called the time-like tube theorem. It's a very beautiful little theorem based on sort of similar arguments to like Riechlider, doing analytic continuation things, blah, blah, blah. The algebras just within this thin, small neighborhood of the world line actually generate the entire type 3 algebra associated with this causal patch. Okay, so naively, you might think that some operator sort of sitting here could sort of come out of here and then fall in here, and the observer over here would never actually be able to see it. But it turns out that's wrong. Like just in QFT, there will always be some signature of the thing here, over here, that you can use, along this whole world line that you can use to work out what it was. This is sort of like HKLL reconstruction in ADS CFT. It's morally the same thing. Okay.
Sorry, just to clarify. So that theorem is in the context of quantum field theory specifically?
It's in the context of quantum field theories. I believe it's only really been proved for flat space. A few months ago, Edward told me he was chatting to a mathematician about doing it for curved space, and it seemed like fine because he wanted to do it to his satisfaction. Yeah, I should check up on what's happening with that paper. Hopefully it comes out, because it will be a lot more readable, I would imagine, than the original literature on this stuff, half of which is not in English. But yeah, it's a QFT theorem.
Okay.
And is this supposed to hold just for any domain of dependence then, where like it's not a
time-like tube is, it's if we have some tube, like is what it's proved for. So certainly, for example, there's a stronger statement you might make that's sort of the strongest form of hard duality, I guess. People mean different things by hard duality. That like any region, then generates the algebra for its entire sort of double commutant. Like, yeah, sorry, that's not domain of dependence. Whatever. Yeah. Anyway. That's not true, at least in free theories. So in 1+1D free theory, if you have sort of a little region up here and a little region up here, then the sort of double commutant, so the thing that's space-like to everything space-like to them, would still be this causal patch. But I could, let's imagine this Minkowski space. I can definitely have something that just sort of goes through here, and the fields up here and down here don't know about it. But for time-like tube, you can't do that. And so that time-like tube one is true for free theories. It's believed to be true for interacting theories, if we could define them, and so on. It's a pretty general statement. Yeah. Okay. Okay, so seemingly we have a QFT algebra that's type 3. But we have a bit more going on here. We're doing quantum gravity, not quantum field theory in de Sitter space. So unlike for a black hole, in de Sitter, there's no asymptotic boundary, so there's no extra physical time shift mode that we can add to the QFT stuff. But we have something new instead. That's again, a quantum gravity thing rather than a quantum field theory thing. And that's the diffeomorphisms in gravity or gauge constraints, right? And so they should be imposed as a gauge constraint and not treated as physical symmetries. So because we're going to a limit where we're considering perturbations in a fixed background, then a lot of that full diffeomorphism invariance gets broken explicitly by the background. But there's still some remaining symmetries, which are the isometries of the space we're interested in. So de Sitter space has some isometry group, and those isometries should be treated as gauge constraints from the physical symmetries, which they would be for say QFT in de Sitter space. So because we've picked out some observer's world line, then that breaks some of those isometries further, breaks them down to the isometries of the static patch. The isometries of the static patch consist of just boosts, time translations of the static patch, basically, and rotations. Okay, so these commute with one another. It's some very simple group. It's just R cross SO D, or whatever, what D minus 1, whatever you're counting D as, D minus 2 maybe. Okay, so the real physical algebra should be the gauge invariant subalgebra of this type 3 QFT algebra. Okay, so it's the algebra of operators in the type 3 QFT algebra that commute with all the commute through the isometries of the static patch. For rotations, this is a perfectly sensible notion. Right, there's some compact group and there's some set of operators in this thing that commute with it, it's fine. However, it turns out that the only operators that are invariant under this boost generator are in fact just multiples of the identity. So this maybe seems like needs some explanation. It's related to the fact that the boost group is not compact. So the trouble is that naively you could try to make a boost invariant operator by taking some seed operator A that's sort of localized here maybe, and then integrating over all possible boosts of it. Okay, so integrating, averaging it maybe over an infinite range from -infinity to infinity of static patch times. The trouble is that any state, QFT state on this de Sitter space, in the very bottom corner and the very top corner, will always just look like a thermal state. Okay, so this average over an infinite range of times will almost entirely be averaging over a state that has a thermal expectation. It just looks like the thermal state. As a result, the operator will always just be equal to its own thermal expectation value. And this non-trivial operator we tried to make is actually just a C number. It's just a multiple of the identity. Okay. So at some level, this is just basic version, sort of restricted version of the standard statement that in quantum gravity, there are no local observables, that everything needs to be addressed to some sort of asymptotic boundary. At another level, however, it's quite clearly complete nonsense and totally unphysical. So I don't know about you guys, but I'm an observer in a theory of quantum gravity, and I don't have access to any asymptotic boundary or anything like that. I don't have a spaceship that can reach the edge of the universe, and yet I'm able to do observations all the time. Okay, so how am I able to do that? Well, the answer is that basically I carry a clock with me. I do observations at a certain time because I do them based on the physical clock that I carry with me and not based on some unphysical background coordinates of my spacetime. So that clock could be, depending on who the observer is, it could be a Rolex, it could be a phone, it could be just our brain. Like our brain is in a different state at different times, and that triggers us to do an observation at a certain time when it's in a certain state and not when it's in another state. But the point is that the measurements are determined by the clock. They're not determined by the background coordinates. Okay, so we want to have the physical result that the observer can do measurements, then we need to give them some sort of clock. Okay, the simplest, stupidest model would just be a classical clock, so some label on their world line that is monotonically increasing as their world line goes forwards in time. Okay, so that will break the boost symmetry. So we'd end up with just the remaining isometries being rotations, and we just get some sort of type 3 algebra. So that's fine. It's a perfectly reasonable story as far as it goes. We still can't define entropies because it's type 3, but that's life. We can do something better. We recognize the fact that whatever degrees of freedom I'm using to sort of tell time and do measurements at specific times rather than averaging over infinite ranges of times has to be quantum mechanical because the universe is quantum mechanical. So rather than adding in some classical clock on the world line, a better model would be to add a quantum clock on the world line. Okay, we'd like this clock to be able to sort of resolve arbitrarily small time periods in the semi-classical limit, and also to be able to resolve like long time periods, to work for a long period of time, much longer than the Sitter time. So pretty much that fixes that the clock has to have a continuous spectrum in the semi-classical limit, and it has to be a spectrum that's sort of unbounded from above. It has to be able to have an infinite range. Yeah, I mean that one's less important maybe, but certainly needs to have continuous spectrum if we want to be able to like tell arbitrarily long times apart and not end up having recurrences that mean we still end up doing this averaging. Okay. So a model for a clock is just going to be that it has a purely continuous spectrum with energy bounded from below. So its Hilbert space is L2 of R plus, it's a half line, and the energy is just the position operator X acting on that thing. Okay. Any questions about that model or why we're introducing it, motivation, anything like that? Okay. Great. So now let's try to understand the algebra of observables of the observer carrying the clock. For the moment, let's forget about the fact that the energy of the clock is meant to be positive on physical grounds, and just say that the Hilbert space of the clock is just L2 of R, and the Hamiltonian is just the position operator. Before we impose any gauge constraints, then the observer's algebra would now be the Q of T algebra A, tensor the algebra of all operators acting on the clock. So the clock's just sitting there, they have access to it, so they can do anything they like with it. Now we want to restrict to gauge invariant operators. So the operators that are invariant under boost. The boost generator is now the sum of two things. Firstly, we have the boost operator acting in the quantum fields. And secondly, we have the Hamiltonian of the clock, the time translation generator of the clock, which is just X. Okay, so we want to restrict the subalgebra of this thing that commutes with H acting on A, H in A, or H acting on the quantum field theory fields, plus X acting on the clock. Turns out that this time, unlike before, we actually do have non-trivial gauge invariant operators. That's great. That's what, physically we thought should happen when we added in the clock. So two obvious examples are firstly just the energy of the clock, right? That commutes with H plus X, because it just is X. And the second one is to take an Q of T operator A, it can be any Q of T operator A, and then conjugate it with e to the minus IPH, where P is the conjugate momentum to X. Okay, so roughly what this is doing, you can think of this P as telling you the time the clock shows at coordinate time 0. Okay, so this is taking some operator at coordinate time and coordinate time t and shifting it so it instead acts at clock time t rather than coordinate time t. That's why it's gauge invariant, because it's defined using clock time rather than the coordinate time. Turns out it's a non-trivial result using something called Takasaki duality, that these two operators generate the entire gauge invariant algebra, subalgebra of this big algebra here. Okay, so what is this algebra? Well, a convenient thing to do to understand what it is to just take this whole algebra and conjugate it by e to the IPH. Okay, that leaves the algebra unchanged. It just lets us view it in a different light. Then these operators are just become A. And so the algebra is generated by the whole Q of T algebra A, together with this operator X, which becomes X minus H once we conjugate it with this thing. Okay, so it's generated by A together with minus X plus H. That should sound somewhat familiar. It's actually exactly the same as the black hole algebra, so long as we identify the energy of the clock with minus the left ADM mass of the black hole, little hl. Okay, so before the algebra was generated by Q of T algebra together with HR equals HL plus H. Now it's A plus minus X plus H. So X is playing the role of minus HL. Okay, so it seems like we again have a type 2 infinity algebra, exactly the same one basically that we had before in the black hole case. Except for one thing, we forgot that the clock was supposed to not be allowed to have arbitrarily negative energy. It was supposed to be bounded from below. It can be convenient to just take it to be bounded from below by 0 energy. Okay, so really X shouldn't be going from minus infinity to infinity. It should be going from 0 to infinity. The real algebra is just a projection of this type 2 infinity algebra we had for the black hole onto X being greater than or equal to 0. Okay, that's a well-defined algebra. You can show that it's a von Neumann algebra. The previous one's a von Neumann algebra. And we can consider now the trace on this projected algebra. So trace inherited from the algebra we had before. But if we substitute in X equals minus HL, then the black hole trace was the integral dx of e to the minus beta x times the expectation of A in, it's now the de Sitter vacuum rather than the Hartle-Hawkey state. The analogous state. Okay, the minus sign showed up because X is equal to minus HL in this identification. However, now we're projecting this algebra so that X has to be greater than or equal to 0. So what that does is it means that this trace is in fact finite for any bounded operator. This expectation value will be finite a bounded function of x, and then this e to the minus b to x integrated from 0 to infinity will always converge and give you a finite answer. So clearly this algebra isn't like type 1D for some finite d, it's an infinite dimensional algebra still, but it has a finite trace, so it must be a type 2-1 algebra. And in fact, it's a type 2-1 factor. Okay, let's briefly, consider what sort of density matrices on this algebra looks like. So in particular, we can consider the maximally mixed state, whose density matrix is the identity. So if the density matrix is in the identity, then expectation value of A is just given by trace of A, so it's just given by this formula. That means the expectation values look like expectation values in the de Sitter vacuum. So it looks like the quantum fields are in the sort of thermal de Sitter vacuum, and the observer's clock has an energy distribution that looks like e to the minus beta h. So the observer's clock is in a thermal state with temperature 1 over beta. So it's worth pausing for a moment to think about this. So in QFT, this state psi is thermal for the algebra on the static patch. Okay, that's the sense in which we traditionally say that it's thermal. And its expectation values, if we have some QFT observable here, then it will still have thermal expectation values. But there's a deeper sense in which that state is actually maximally mixed. Okay, so what's happening is that you can think of this as like there's some sort of extra bath, and that bath, think about the microcanonical ensemble of states in a Hilbert space. Okay, it's maximally mixed within the fixed energy subspace. Each state has equal probability within the fixed energy subspace. But if we just look at operators acting on some small subsystem, then the expectation values of those operators will be thermal. Okay, so that's exactly what's happening here. We have thermal expectation values for the state, but actually empty de Sitter space is really maximally mixed. So this explains an old observation from people 20 years ago or so, that if you perturb de Sitter space in any way, you always end up decreasing generalized entropy. Whatever you try to do, you can try to sort of increase the entropy of the quantum fields, but that makes the area smaller. You can try to increase the area by putting negative energy in there, but that makes the entropy smaller. Whatever you do, you always end up decreasing the generalized entropy. The reason is that it's a type 2-1 algebra, and empty de Sitter space is already maximally mixed. So whatever you put in there is making it have smaller entropy. Okay, I am almost done, but I want to very briefly talk about some ongoing work with Edward that we're currently writing up. It should hopefully be out pretty soon. And that's talking about JT gravity. So one sort of big disadvantage of the constructions I've talked about in the paper so far is that we really had to take a semi-classical limit, so the geometry was basically completely fixed. Like maybe there was some boundary time that could fluctuate, but the actual real geometry was fixed. And you couldn't have sort of, all the wormholes were short. Everything just looked like a two-sided black hole. And we had to use a different we also had to use, for example, a different algebra for each possible size black hole. It's very sort of specific to one particular geometry. So JT gravity plus matter at finite temperature, but not including higher topology corrections, is a very nice setup because we have an infinite entanglement entropy. This infinite entanglement entropy is sort of coming from this topological term S0 in the JT gravity action. So that means that our algebra should be indeed really type 2 and not type 1, but we can still have fluctuating geometry. And the way we can have fluctuating geometry is that the sort of two boundaries can fluctuate in interesting ways. So I've just drawn an example here. You can have some state with sort of a load of matter sitting in the middle that then has what's called a long wormhole. So sort of a light ray shot out from here in the absence of matter would end up almost hitting the boundary, right boundary up here. So the right boundary would sort of go from here all the way down to here. But if there's a load of matter sitting in the middle, then you can have focusing and you can have the right boundary way off over there. Okay, so you can have much more interesting states going on. You can have interesting dilaton profiles and so on, and cool stuff happening. Okay, so we'd like to understand the algebra observables in this theory. So because the boundary is fluctuating, there's no longer a sort of fixed bulk region that is visible from one of the boundaries, right? Before we sort of had some fixed, one causal wedge was visible for the right boundary, and then the complementary wedge was visible from the left boundary. Now we don't have anything like that. At some point here, depending on the state of the boundaries, could be visible from the left, it could be visible from the right, anything could happen. It could be visible from neither naively. So we don't just sort of have some fixed bulk region that we start with, but we can still define a boundary algebra in the following way. First thing we have, if we have sort of bulk operators sitting at the location of the right boundary, whatever it is, it's sort of little t equals 0. Okay, that's one operator we can use. So that will depend on how far away the boundary is. There's some, depending on the sort of conformal weight of the operator, delta of the operator, then it will get rescaled depending on how far away the boundary particle is. But it's a well-defined operator. And then the other thing we have is the sort of right boundary Hamiltonian, say. Okay. And we can consider an algebra generated by those two things. And that's the sort of full right algebra of things we can measure at the right boundary. Turns out that this algebra, again, appears to be a type 2 infinity factor. And we also have that the two boundary algebras are each other's commutants, and there's sort of a nice thing that goes through. Because it's a type 2 infinity factor, has a unique trace. And it turns out that this unique trace is basically taking the infinite temperature limit of the expectation value in the Harder-Hawking state. Okay, the Harder-Hawking state is sort of the state you'd get with the Euclidean path integral. And so that leads, when you do this, then you end up getting entropies that exactly agree with the sort of Euclidean gravity calculations. But again, they're now actual statistical entropies for some algebra. They're not just some Euclidean computation that we call an entropy. So that's pretty cool. In particular, I want to emphasize the importance of including matter here. So we could have done the same thing for JT gravity without matter. Okay. In that case, we would have had that the right boundary algebra consists of bounded functions of the right Hamiltonian. Okay, the right ADM mass. So that was actually talked about in a nice paper by Jaffrus and Harlow a few years back. But the important point is that if the algebra is commutative, then any positive linear functional in that algebra has sort of expectation of AB equals expectation of BA. And so any linear functional is an equally valid trace. In fact, that means that you can say that entropies with respect to the algebra can be pretty much anything you want, depending on the trace you define. Okay, so if you want to have the entropies match Euclidean gravity answers, you need to sort of put in the right trace as like extra data in the theory. It doesn't just follow from the ordinary theory of JT gravity without matter. But JT gravity with matter, that's not true. And you're sort of forced into this unique trace that agrees with the Euclidean gravity answers. So I think that's a really cool story. I find it really satisfying that this is, the Bekenstein-Hawking entropy and quantum corrections to it and so on. Like this JT gravity entropy includes large corrections at low temperatures. It really all just does come from algebraic stuff, but you need sort of enough algebraic stuff to be getting like Hawking radiation and things like that. Otherwise it just, the theory doesn't know about it. Okay, so I think that's basically everything I'm going to talk about. But for anyone who got completely lost by how fast I was going to try and cover all the content, or just got bored and zoned out, then maybe you can zone back in and I'll just say a few final words. So yeah, what's the takeaway from all this? It's really that Lorentzian semi-classical gravity does know not just about the Bekenstein-Hawking entropy in a classical thermodynamic sense, but it knows that it really is a statistical entropy. You have to throw some moderately powerful maths at it to get it to admit to that fact, but it really does know it all along. The other big takeaway is that even though it has quantum fields in a finite temperature thermal state, there's a deeper sense in which in quantum gravity, the de Sitter vacuum is actually maximally mixed on the static patch. And that's why you can't make its entropy bigger. In terms of where do we go from here? well, it seems like perturbative gravity, or quantum gravity in the semi-classical limit is enough to get you from a type 3 algebra to a type 2 algebra. Of course, non-perturbatively, the Bekenstein-Hawkey entropy is supposed to be finite, so we should really have type 1 algebra. Presumably, getting from type 2 to type 1 is going to be a lot harder than getting type 3 to type 2, even though it's just taking away the same number of i's. Some part of that story seems to be wormholes. We've learned a lot about what they do for us in terms of, seeing the finiteness, the Bekenstein-Hawkey entropy, and so on. But I don't think it's all of it. In particular, wormholes are sort of consistent with some sort of ensemble theory stuff. And to really get a type 1 algebra, that's really about sort of not having an ensemble and just getting like the CFT algebra at finite n. So yeah, I think that's obviously very, very hard. That's solving non-perturbative quantum gravity, whatever you want to say. Like obviously, far off from that, there's a lot of interesting stuff like wormholes that you can do that won't get us all the way there, that making interesting progress on it. But I think there's also really interesting physics that we can see at the sort of type 2 stage. We can see before going to crazy non-perturbative stuff. So there's loads of stuff that we've been doing that I didn't talk about today, some of which is in published papers, some of which is not. So you can understand the generalized second law in a very simple way in terms of easy little entropy inequality for these type 2 von Neumann algebras. You can understand sort of scrambling physics using so-called free product algebras, and you get a whole load of interesting stuff from that, including some interesting stuff about how the QES prescription and non-perturbative corrections work to that we didn't know about before, and be interesting now going to derive from Euclidean gravity because we hadn't found that there yet. There's also super interesting stuff in super JT gravity. So Juan and people had a paper on that this summer. You can look at that all from a sort of very canonically quantized algebraic perspective. They were doing path integrals mostly, but you get some really interesting stuff and cool algebras and cool states that have zero. You prove that there's states that have zero energy on both sides of the wormhole, zero ADM mass on each side, but they have totally non-supersymmetric, like long representation, not BPS matter sitting in the middle. So that's really interesting stuff, I think. Yeah, these are just like super cool, powerful mathematical tools that let you do some cool things. I encourage people to play around them. I'm sure there's loads of stuff we haven't said that is there to say. Tom Faulkner put out a cool seeming paper last week using this stuff that I have yet to understand, but seems very cool. Yeah, that's all I have to say. Thanks a lot for having me talk.
Hey, thanks for the very nice talk, Geoff. Any questions for him?
Yeah, I guess I'll ask a question. So can you, I mean, all this mathematical structure that's coming out, I mean, it seems like it should be suggesting what direction we should go if we wanted to have some models, or at least toy models of how we would describe de Sitter microscopically, or a version of holography that describes de Sitter. I mean, we're seeing some aspects of the structure that it should have. I mean, does this tell you how to make a toy model?
No, it gives you something that if you have your toy model, then you can like look for this in it in the sort of large semi-classical limit and understand where it's coming from, and that's a good test of a toy model, I think, if you have it.
Right.
In terms of hints of what the toy model should be, I think there's a couple of ways you can think about how it should happen. One is that it's like the sort of two-sided black hole case, and there's some finite n algebras, and these semi-classical algebras are approximating them, and the entropy of the semi-classical algebras is the entropy of the finite n algebras. There's actually a very different story that happens for one-sided black holes in ADS. So they're at any finite n, then they sort of have zero entropy. But in the large n limit, you still have, if you do things in the right way, you still have a sort of type 2 algebra that still has an entropy that's the Bekenstein-Hawkey entropy. And what's happening there is that basically the operators that let you see the state as pure become infinitely complex in the large n limit. And so there's a sort of, there's an approximate algebra or like a coarse-grained sort of algebra where you're not allowed to take too many products at finite n that has some entropy at finite n. And in the large n limit, that becomes like actually an algebra. And then the entropy becomes, rather than some sort of coarse-grained entropy, it becomes like an actual algebraic entropy. So if I had to put money on it, I would guess that de Sitter is sort of something like that, where non-perturbatively you can at most define some sort of approximate algebra where you don't push it too hard, blah, 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 and some sort of coarse-grained and approximate notion of entropy. And then that becomes this really well-defined entropy in the semi-classical limit. So, I don't know the details how that will work. Like, I think there's probably some, I think that whatever that finite n entropy is, it's somehow getting bounded. I think that has to be a big clue, and we have to be taking it seriously. It's bounded, and there's some, the sort of empty de Sitter space is making it as big as possible and is maximally mixed on it. But yeah, this is, I don't think it's immediately going to let us solve non-perturbative quantum gravity in de Sitter space, that's for sure. If you're Lenny or whatever, and you have some toy model you like that has two entangled systems describing each static patch, that can totally be consistent with that story. This story, I'm always slightly suspicious of those sort of toy models, but I would say the fact that this stuff works makes me mildly less suspicious of them. I'm still suspicious of them, but this is certainly consistent with them. Well, one thing
those
is
things
the fact that we
have
needed the observer. I think the fact that we need the observer to get this algebra at all is really quite key. And so that's going against that. It makes me think that the sort of approximate algebra is really a very observer defined thing. And that's all I say.
There should be something, right? There should be something there that, I guess, like the observer or like your choice of static patch that gives you a different algebra for different different construction for different patches or different observers. I've
always been secretly sympathetic to the idea that the Hilbert space of closed universes in quantum gravity really should be one-dimensional, and this is what solves factorization problem and everything. And if you believe that, you can still have interesting physics in a one-dimensional Hilbert space if there's interesting definite maps from like observables, physical observables, to like actual things. But to actually have an algebra, you would need to do some sort of gauge fixing clearly in that setup, some sort of like, adding in an observer or something. You could imagine a one-dimensional Hilbert space, but then you condition on an observer being present in it, and then you get some sort of non-trivial Hilbert space. I think there's things that could be said like that, that this is hinting towards, but I don't know. The framework for doing that sort of stuff seems very hard. People have said a lot of things about relational quantum mechanics over the years. I haven't read most of them, but I don't get the impression that any particularly magic, like nice, clean framework has come out of it. It seems sort of messy and nasty. I don't know. Yeah.
You mentioned at the end there about scrambling physics, that there were results in the algebraic framework that have not been understood from the Euclidean framework. Can you say a bit more about that?
Yeah, this is so we have this idea that if we're computing Rayleigh entropies, then we should sum over saddles. We can compute stuff very explicitly using this algebraic framework for sort of series long wormholes created by shocks, and what you get is, for the Rayleigh entropy, looks like a sum over saddles associated with different extremal surfaces, except some of the extremal surfaces contribute with a minus sign, and the extremal surfaces that do are what are sometimes called, or I sometimes call bulge extremal surfaces, which means they're not locally minimal on some Cauchy slice in terms of generalized entropy. So if you sort of look through a Cauchy slice through the whole wormhole, it sort of gets big, smaller, bigger, smaller, bigger. The points where it's like maximal size are the ones that contribute with the minus sign. So this is very related physically. You know, the reason this shows up is very related to a paper by Jembin and Douglas, and I think Shunyu from maybe a year and a bit ago. It's about like subleading Weingarten stuff in like unitary ensembles. And they understood it in a very narrow context in gravity. But this is suggesting pretty strongly that there should be some more general sense in which these negative signs, at least in Rayleigh entropies, are coming from these different sorts of quantum extremal surfaces. So yeah, that's something that I'm keen to try and understand from a gravity point of view. I think Jembin thinks there might be some way that it follows from similar physics to their physics, but nobody's really understood an argument for that. So that's very interesting. Yeah.
Okay, thanks. Any other questions? Okay, if not, let's thank Geoff again. Let me stop the recording.